Hi there, this video is going to measure capacitance of a human body both in a DC circuit with a multimeter and also in an AC circuit with a 20 volt peak to peak sine wave coming out of this signal generator. So we've got a series circuit. When the opposition to current flow for the capacitor and the inductor are equal, they're equal in opposite phase, they'll cancel each other out, and the only opposition to current flow in the circuit will be the resistor, and you'll get peak current at that particular time. From the oscilloscope, we measure the voltage effectively to get the peak current. So when the output voltage here is in phase with the voltage going into it, we can see here the zero phase shift between the output and the input. That's effectively resonance. If we go lower frequency, we can see significant phase shift, so that's not resonance because they're not in phase. If we crank it up a bit with reasonable eyesight, we can see at that point there the waveforms are in phase. So at that point, the opposition to current flow from the capacitor and inductor are equal and opposite, and they cancel each other out. And that's why you get in phase voltage across the resistor. So we've got a circuit here of 10 nanofarads, 4.7 millihenries and 1K. So we can see the resonance with 10 nanofarads is 24 kilohertz. We take the capacitor out, now what we're going to do is put the human body in, going hand to hand, and we can see we've got significant phase shift here. So what I'm going to do is up the voltage, so it's clearer. We're going to change the time base. We've got significant phase shift. So if I increase the frequency, let's increase it up to about 70 odd. Are we getting phase shift there? Not much, that's pretty close. If we increase it again, if we go significantly the other way, so increase it, that's pretty in phase there, and we can read off 64.5 kilohertz. Let's call it 65 kilohertz, and from that we can work out what the capacitance is. So if we work backwards from the resonant frequency, we can work out capacitance from this formula here. So we have a table here, and that table is showing the resonant frequency where we had here was 65 kilohertz. From this table here, we can see that the capacitance of the body is 1.28 nanofarads if you go through the calculation. So going hand to hand across the chest, the capacitance, its resonant frequency is 65 kilohertz. That means that the capacitance of the human body is 1.28 nanofarads. Okay, so what if we just take this meter, so this is a DC meter, if we connect the leads together, we're on 200 nanofarads, we'll go down to the lower scale, onto 2 nanofarads. It won't read there because you shorted it out, okay? So if I do the same thing, I go hand to hand, okay, it's reading above 2 nanofarads. If I put it up a scale, so on DC, it reads different values. It's reading 13, 14 nanofarads on a DC system. So the body does react biologically to different forms of electricity in terms of DC and AC. So on AC it was about 1 nanofarad. On this DC setting it is 13 nanofarads. And just to show, if we put the 10 nanofarad in on DC, it does read, okay, it's a little bit low, it's nominally 10 nanofarads, but it's reading 8.35, so it's reading a little bit low. So to summarize, the capacitance of the human body in an AC circuit is about in the region of 1 nanofarad. In a DC circuit, it has a different scale order. It's effectively multiplied by 10. So the body is a capacitor. Capacitance is a natural effect because you can essentially charge yourself up with electrons. So we've measured capacitance of a human body 2 ways by experiment.